will start in minute. Oh. One moment. Lazy computer, work faster. Move, you lazy computer. Come on, computer. Добрый. Ой, кусок дерьма, а не компьютер. Как это так? Что наделано? Бред какой-то. И это ж какой-то бред. Vienmēr pienāk pirmā reize. Нет. С возрастом плохо видишь вблизи, а очки носить в лом. А вот так видно. Реклама все накрутится по телевидению. Этих оптики. Вот там к мужику две девицы ходят ему баночку оливок. Так вот. Vienmēr pienāk pirmā reize. are 5 minutes behind schedule. Okay. I need to go fast because I have to attend one more meeting. Okay, where we are. Let's continue our Analogue preprocessing part. Where the problem is, before we can do any numerical processing, even before analog to digital conversion, we need to perform some analog preprocessing on our signal. If we take a look on a frequency chart, here I will put it in red, it's 1/2 of sampling frequency. 1 divided by space between samples. I may use tau. If you speak filtering, the red line marks Nyquist frequency. Anything, any signal here on the right side of the red line will cause distortion, will cause error, will cause malfunction. Because no digital system in this world can correctly work with signal above the Nyquist frequency. So it's a red line. We need, look here. Here, for example, let's take an outline at 50 Hz. Your base signal you need to process. Actual range from 48 to 53 is sufficient for small, let's say, for common application. But if you look deeper, you may need 150 for case of Earth's fault protection, especially it's for distribution network. If you would like to have precise detection of current transformer saturation, 250, maybe 350, and so on. And what's important? In this area, you may want to have flat characteristic of your analog preprocessing part. And it should have at last 20% safety gap before Nyquist frequency. It's important. Safety gap is important. So ideal, this white line shows ideal preprocessing, ideal characteristic of this preprocessing part. We need to exclude, to suppress signals with frequencies beyond Nyquist frequency. And we need to maintain, to ensure controlled error in, at last, in green area. We should not introduce magnitude error, and angular errors are not welcome. First, of course, first choice, how to say it? First step is a Butterworth filter. Base for the Butterworth
the Butterworth filter. Problem with Butterworth filter, actually first stop with the Butterworth. Problem with Butterworth, it has a very good steady magnitude function. But one problem with Butterworth, if your signal is step, you have transient. Butterworth filter will not produce the step. Butterworth filter will overshoot. So high order Butterworth filters are not very good on transients. If we have, we are sure what we will suppress this or compensate this in numerical part, it's okay. But high order Butterworth filters, they have this, how to say, disadvantage of overshoot on transients. Another alternative is a Chebyshev kind of polynomial. One more thing is better word. High order. You may find better word very lucrative on high order, but high order better word filters, they do have complex conjugated roots, and they require coils. Low order can be done with only RC. But high order Butterworth filters require coils, and we hit necessity of high stability, precise coils, expensive thing. Okay, next. Next step is Chebyshev polynomials. Chebyshev filters. Based on Chebyshev filters, it's so-called Chebyshev polynomial series with minimal difference from minimal distance from one. Chebyshev polynomials are not so uniform on path zone, but Chebyshev Chebyshev isn't very popular, but Chebyshev, for some designs, do prefer Chebyshev because Chebyshevs allow fast cut. Chebyshev can be good in how to say, in this area. Chebyshev can allow you fast slow. Fast slow. So Chebyshev's polynomials cosine and arc cos x here 0 x, so if x between 1 and 0 and arc hyperbolic cosinus of x for x greater than 1. Here is common form for Chebyshev polynomials. For n1, d1 will be x itself, second order equals to 2x squared minus 1, 4x cubed minus 3x, and for number 4, 8x power 4 minus 8x squared plus 1. Here are typical Chebyshev polynomials. So while x is between 0 and 1, absolute value of polynomial will be between 0 and 1, and above it will grow steadily. For case of filter, you dance with characteristic square of transient function model equals to 0 squared divided by 1 plus epsilon square and order polynomial mix. This factor should be selected in such way that at 0 point transfer function, absolute value of transfer function module square should be equal to so if you do so, it's at DC point. You will see K1 for even n double I minus 1 and 1 plus epsilon square for n being double E. Or I from 1 theoretical to infinity. This factor epsilon, it defines for you how to say non-uniformity of characteristics. Characteristics of Chebyshev filter isn't straight line, but ideal characteristic is like this: frequency model of transfer function. Ideal here, let's say 1, here 0. Chebyshev will give you kind of waving. So this line will be H max and bottom H min. This ratio for Chebyshev filter equals to 1 plus epsilon squared. So with selection of this parameter, you can select non-uniformity. I can tell one thing, if you use Chebyshev design, you can do one trick. You can select, you can play with factors. So let's say this will be at 50 Hz. should be noted for what h max equals to a0 squared 1 for us epsilon squared, h minimum sorry, h0 it's 0.4 and the double for odd orders. For even orders, again, h max is h0 and h minimum will be h0 divided by square root 1 plus epsilon squared. This is for cases double I for even orders. I can show simple, just for understanding, if uniformity 0.5 decibel, 2 decibel, 3 decibel, non-uniformity, h max h min 1059 1250 and 1413. For this case, k should be 122 1250 and 1995. Epsilon 0349 0765 0998. Here, non-uniformity. For practical purpose, Chebyshev's coefficients are derived from Butterworth. It's easier not to calculate them directly, but obtain them as a derivative from known Butterworth factors. In reality, today we have plenty abundance of software solvers for creating these factors. Okay, for all orders. Добрый день. Как мне нравится это слово. Да? Теперь это будет. А куда я? А что делать? Ладно. Если бы моя фамилия была Рябинский, да. Так, окей. 1 divided by square minus cosine square 2i p divided by double n double multiplied by hash gamma multiplied by cosine double I minus 1 and divided by double n. All this for I starting from 1 to and divided by half. This, this is for odd. Yeah, gamma is 1 divided by order, arc hyperbolic, and 1 divided by epsilon. Yeah. For we will get 0 1 divided by gamma and should be 1 divided by hyperbolic cosinus of gamma square minus cosine square I minus 1 p divided by n. And demon double bi hyperbolic sine of gamma multiplied by cosine I minus 1 p divided by n. This enforce for I starting from 2 and ending to n plus 1 divided divided by half. Where is, oh, okay. Ah, this looks like hell. It's interesting. What it is used worthless to work with orders higher than 4. Why all this? Later I will bring common table of ready-made factors. They all are calculated. This thing, what's good? Chebyshev filter ensures better cutoff. It has, how to say, stiffer slope from pass to reject. But Chebyshev filter may perform worse on transient. Chebyshev filters appear when they appear. Chebyshev filter appear when you need a very stiff border between pass, go not go, between pass and reject area. On the slope, Chebyshev perform better. One more thing. What can be done with Chebyshev filter? One trick, there are special designs for Chebyshev filters with 0 point in the area just above cutoff frequency. Color design is special Chebyshev filter with 0 points just above this rejection frequency. It in color design ensures faster possible transfer from go to no go. Color filters yields very sharp cutoff on frequency. In times where processors were expensive, the higher performance of our system, the higher is possible, how to say, higher sampling rate we can afford. The higher sampling rate shifts to the left border of allowable frequency range. This reduced, how to say, this eases requirements for analog preprocessing. Cheap or I don't know, some kind of special processor and digital part means what we cannot afford high sampling rate. Low sampling rate means what Nyquist frequency is closer to our working area. And we need, actually, with complex filter, we can do what? We can ease task for our processor. We can reduce requirements for digital parts by analog preprocessing, by complex analog preprocessing. Okay. No, I have one problem. I need to attend another meeting at in 10 minutes. Okay, I will shift it to left. There also are Bessel polynomials. I will bring a large universal table with factors, filter factors. But in general, today you can easily find filter design software. Key work, filter factors are not problem. What the problem is? First, you need to strictly define where will be working frequency of your device. For ordinary relays, you need your precise area is narrow, around 50 Hz, around base frequency. Special case, one special case when your head S will be it's a hydropower. For hydro generators, remember, for hydro turbines, working frequency range is from 10% approximately of nominal up to 120%. It's a working allowable frequency range for hydro turbine. Same thing with some wind turbine. Not all. Not any wind turbine can operate in such a wide range. But for hydro, remember, upper is special painful case, earth fault protection for hydro generators. It uses third harmonic. So operation range here will be approximately 5-3. And you need to be precise. Stupid type of relays are simple, use very simple approach. They disable earth fault protection function if generator is not synchronized with network. But it's not a good idea. Another moment very is power line carrier application. When network is used as a data medium. Okay, it's bandpass filter. But for special idea, earth fault protection. Earth fault protection will put high requirements on frequency range and one more problem. Different area, special area, very tricky. Differential protection based on third harmonics. They are used for large scale generators when levels of third this protection device when they are needed. It's an earth fault protection for generators. It compares levels of third harmonic difference on the neutral side and the network side of generator. High requirements on filter. They should have good characteristic in phase area and they should effectively suppress low frequency components. Okay, it can be done with numeric part and components around approximately 7 times, approximately 300, above 350 Hz. All this should be suppressed. So high requirements for filter uniformity. Okay, bad news, I have to finish today. Next time I need to find a good example of these charts. to explain this filter. It's okay. Passive filter and some examples how it can be done. Really, today people are lazy and use ready software. But really, creation of optimal filter is a tricky thing, and you may find it's modern design. It's like new. It has nice button. This analog preprocessing part is a heritage from 70s. Designed one, don't touch it. One more thing. When we will speak on digital part, on Fourier transform, I will show you one tricky thing about Fourier transforms. Side lobes. And fight with side lobes. Nothing, how to say, to be used. Seeing fight with side lobes with analog preprocessing. You're always balancing. You're balancing your digital part, expenses of your digital part, with analog preprocessing. You can ease task of your processor. I saw devices where processors were so weak what multiplication were done in analog part, in preprocessing. If they needed to multiply current by constant, so this current by constant was done in analog part to diminish load on numerical part.